All right, good evening and welcome to all the participants. Today is the 17th lecture of the online interactive lecture series, which is being organized by the India-based Neutrino Observatory. This lecture series we began in, I think, April 27th of April, and many people have given interesting talks on different aspects on not only neutrino physics, but also topics like dark matter and I think other subjects. And I would like to encourage you to visit the website that we have developed for this one, which is being currently shown on the screen. I think Dr. Satya is not showing the screen. All right. Yeah. Just a minute. Yeah, so we will share that screen soon. And so we also have a Facebook handle and Twitter handle, and we encourage you to visit those pages. Today's speaker is a very special person. In fact, he was the one who was moderating this session for quite some time, and today I have the pleasure of introducing him to you. He's none other than Dr. V. Satyanarayana. Dr. Satyanarayana did his BTech in Electronics and Communication Engineering from JNT University, Hyderabad, and PhD in Physics from IIT Bombay. He is working in the Department of High Energy Physics, TIFR, since 1983, and is currently a scientific officer, H. He is also a visiting professor at the Applied Science Department of the American College, Madurai. His areas of interest include detectors and instrumentation for high energy and nuclear physics experiments. He worked on many major experiments, including a series of underground experiments at Kolar Goldfields, D0 experiment at Fermilab, Chicago, and CMS experiment at LHC at CERN, Geneva. Currently, he is fully engaged in building a mega science experiment called ICAL at the proposed India-based Neutrino Observatory, INO, near Madurai. And of course, he has vast experience in detectors called as resistive plate chambers. He started by designing this one feet by 1 feet resistive plate chambers, and then upgraded to 1 meter by 1 meter, and now I think 2 meter by 2 meter and multi-cap RPCs. And as you must be aware, INO is a mega science project, and I must emphasize here that it is not just only a physics project, it's also an engineering project. So these resistive plate chambers, in which Dr. Satyanarayana has a lot of expertise, are sensitive detectors that will detect the signal left by the neutrinos. So without the resistive plate chambers, there is no ICAL. I invite Dr. Satyanarayana to share his excitement of developing these resistive plate chambers. Over to Dr. Satyanarayana.
Good evening, everybody. Can you hear me? Can you hear me?
Yes.
Okay. Also, can you see the screen?
Yes.
Okay. Thank you, Deepak, for nice introduction. And also thanks a lot to Rajaji and also Acharya who are on the call. I think I also see a few other friends from INO. As Deepak has introduced, of course, we have been having these talks now for a while. And most of them have been, of course, given by a real expert in the field of neutrinos and dark matter and whatnot. And of course, we also had a few talks on the experimental techniques as well, but they have been largely on the theoretical aspects of neutrinos. In fact, incidentally, today should have been given by one of our past INO students. Somehow I was not able to get him on call. So as it always happens that I have to pitch in to give this in the last minute. I hope I'll be able to kind of satisfy your requirements in terms of knowing about what these resistive plate chambers are and how they are used in ICAL built by INO experiment and also other experiments. Okay, so the title of my talk, as you see on the screen, is how will the INO detector record the neutrino interactions? That the title is motivated because you have been hearing about neutrino oscillation, neutrino interactions, and various other phenomena. But when you really build INO, the big detector, and how actually whenever the neutrino interactions do happen in your detector, of course, they are reasonably rare and they're not in big numbers. So how will you actually end up recording them, and how do you know that your detector is live and working to record the data, and also how do you know that the detector is recording it accurately in the sense that it's not a spurious event and so on. Okay, so that is the kind of motivation for this talk. What you see on the left, of course, you will see this picture many times later, but this is the so-called iron calorimeter detector of proposed INO project. And on the right, of course, I gave symbolically some blocks of what it looks like, some kind of electronics. And of course, this we all know is a kind of cable. Some of us call it flat cable because it is in flat and there are multiple conductors. So the point is, how do when neutrino interactions or any interesting phenomena happens, how do you actually record them? So that is the theme of today's talk. But obviously, we must start when you talk about something recording. Of course, we should go back all the way to 1956 and a little bit look at maybe just to get the context how Reines and Cohen, the guys who actually discovered neutrino, the very first discovery experiment in 1956, did that using today looking back, it looked like a very, very simple rudimentary experiment, but nevertheless, if you look at the kind of numbers they obtained with their measurements are phenomenal. Look at this at the bottom. So of course they used anti-neutrinos which are coming from a reactor. So this is incident at anti-neutrinos which are coming through this port. Okay, and this is your nuclear reactor. And what they have is a detector like this, which is actually made of about 200 liters of water, about 40 kilograms of cadmium chloride. And looking at this, the whole thing, these circular objects are, of course, photomultiplier tubes, which are supposed to be about 5-inch in diameter, about 100 of them, 110 of them are used. So when you see an antineutrino coming in and then, getting into the volume, which is actually a scintillator volume here, you get a, inverse beta decay, you get a positron here, and which is actually pass a little bit beyond in this volume, detector volume, before it interacts with an electron and producing, they annihilate with each other and producing two gammas back to back. So this is the first event, you can say prompt event. So this is what is given here, antineutrino coming with proton producing, of course, a neutron and then a positron. Now, this positron with electron producing two gammas, and you need to detect these two gammas first in order to kind of say, yeah, this is my starting point, this is the prompt. And after some time, the delayed coincidence of the neutron with cadmium is going to kind of produce, let us say, photons, but those photons is depending on the fact that there is a delay, which is actually shown here by a zigzag movement here. Now, these gammas are photons that are produced after a delay of roughly 3 microseconds. Again, in coincidence with the fact that you have two gammas here, has to be recorded correctly in sequence. Then you'll know that these gamma came, let us say, roughly 3 microseconds after these two gammas which were prompt. Now, these detecting the first two gammas, and then in coincidence with the delayed neutron capture, which is actually giving you the gammas that are delayed. combined together with due to neutron capture. So combined together is what is going to give you a very unambiguous fact that is actually an interaction coming from inverse beta decay. Okay, so this was way back in 1956, but maybe 10 years later, 9 years later, in 1965, some of my senior colleagues from the department actually built a large number of spectrographs, what are shown here. There are many of them. It's almost about 2.3 kilometers below the Earth. And here, this particular detector that is actually showing is so-called telescope 2. And let us go to the next slide to kind of say a little more detail about what it is. A schematic of that is actually shown here. Okay, so it's all vertical looking detector. Okay, you can kind of see. So there are, let us say, 3 vertical walls which are made of neon flash tubes. So the flash tubes are actually long, like old tube lights, very thin, maybe about a centimeter or less. But you can see they are sticking perpendicular to your screens. And the black ones here is lead, which is about 1 inch thick lead. And on either side here, which is slantedly hashed, they are the scintillators. So if you want to connect them up here, there are scintillators here. There are center line, as I told you, there are 3 layers of the neon flash tubes and also the lead that is coming in between. Now here, of course, they recorded a neutrino interaction that's taking place. Let us say neutrino coming from rock and entering at an angle which is very, very large angle. You can kind of see here, and then leaving a track on this here, and also another track which is actually caused by, let's say, muon decay from the W. So you have the muon that is produced here, and also this is a decayed muon, okay, which is also a line which is drawn here. And these dots that are going through the neon flash tubes, they're actually, they flash, they give light when any charge particle kind of passes through. So if you connect them, those, those in line, you actually see a very nice straight lines here. And this is all, what is hashed here is all rock. And the way, to record the data when this event has actually happened, you actually hang a wall clock onto the detector and take a photograph, because this is the detector signals are actually flash of light. So along with that, you also see what is the date, what is time. You can see 30th May 1965, and also the time that is given. So in 1965, August 15th, in fact, the first detection of muons which are produced by cosmic ray neutrinos deep underground, that was detected. And so this is, so in some sense, of course, we are definitely pioneers in neutrino physics. That first atmospheric neutrino was actually discovered in polar goldfields by Tata Institute and the group from Osaka City and Durham group. Okay, now why I brought up and showed you these 2 interesting experiments to kind of tell you that to do great physics, to do physics which is of potential of Nobel Prize, you don't really require a great high tech or whatever, but what is actually important is the idea of how you design an experiment. Both these experiments, both Raynaud's experiment as well as KGF experiments, the detection, the data acquisition, the electronics, etc. If you look at, you will be surprised, because this one uses an oscilloscope to capture the signals produced by the prompt photons and then the delayed, the neutron capture. Whereas this one actually uses ordinary camera. Of course, it's a mechanized camera to kind of capture the flashes of light that is coming from the neon flash tube. So this is what I wanted to tell you. It's all depends on how cleverly experimentalists put up an experiment. That is what is more important than really using, very, very high speed clocks, large memories and whatever. So, okay. So that is the idea, but let us now come straight to, decades later. We have proposed an INO laboratory. Today's talk is, of course, on the INO project. This is near, this is a laboratory complex we were planning to build, construct between a place called Bodhi, okay, and it is about 100 kilometers west of Madurai, between Kerala and Tamil Nadu border. what we want to do is, if you can actually see on the top, there is a backdrop that is given a hill called West Body Hills, and we want to kind of dig a tunnel through that, roughly about 2 kilometers long tunnel. So this is the end of the tunnel, and then you build a large cavern here. The cavern sizes are very, very large, about 130 meters long, and maybe about 30 meters by about 26 meters cross section, in which we want to house, if possible, 2 large detectors. One, what you see here in yellow color, is the one that we are going to describe soon. And there is also place for constructing another detector here. Apart from that, there are also other caverns meant for other underground facilities. One here, it is expected to have a neutrino-less double beta decay experiment, which sometime back Professor Vandana Nanal talked about. And here we would like also keep a place for a dark matter experiment. Dark matter physics, in fact, was talked other day by Vasudev Das Gupta. So it's a tunnel. So I mean, it's a large cavern cross section. So there will be 2 tracks. So, one track going, one track coming. That is the kind of size of this tunnel that can bring you here. And so this is going to be a underground complex, not only for neutrino experiments, but also all futuristic experiments. Could be NDBD, could be dark matter, could be some material science, maybe geology, maybe some biology experiment. So this is a national facility where we want to build such a unique facility, at par with some of the best underground labs in the world. Now, coming to the so-called iron calorimeter, which I briefly mentioned where it is going to occupy this place, is actually why we chose this particular, how we chose this particular detector. We wanted to, of course, use magnetized iron as the target mass for the neutrinos, and use resistive plate chambers, where we describe in detail later, as the active detector elements. The detector elements are the ones which are going to detect the charged particles when neutrino interaction take place inside the magnetized iron, which is target mass. Of course, we use at the source of neutrinos, we use atmospheric neutrinos, which are free to use. They're not, they're all the time there. They're available for us 24/7. And since atmospheric neutrinos have a large length, large L, and also the E range, which you must have heard many times about when you talk about neutrino oscillation parameters, you always have this expression as L by E, many speakers talked about. So the iCal will use very, very large target mass as well. So the mass that I shown there is of the order of about 50,000 tons in the current design. And there is also a place for another 50,000 ton detector if required. We want to cover neutrinos coming from all directions, 4 pi coverage angle. So we have, except in real, of course, horizontal, because the way we build this detector, near horizontal will be difficult to get the coverage. Now, up to about 20 GeV muons contained inside the detector, what you call fiducial volume. And most interesting region out of this is about 5 to 15 GeV in the kind of sector that we want to probe. Obviously, we want to have very, very good tracking as well as energy resolutions. Remember that we want to measure energy. Also, we want to measure the length, so we require the tracking. We see these details a little later. So we want to get the timing resolution if you want to distinguish neutrinos coming from down or up to discriminate, and hence you want to get a good directionality, you should be able to kind of track the charged particles traveling through your detector at a resolution of 1 nanometer. So this is like having a stopwatch. Instead of having milliseconds resolution that you have in Olympics, maybe tens of milliseconds, you would like to have nanosecond time resolution. Of course, you need to, this is magnetized detector, so you will be able to get a good charge resolution, whether the charged particles produce a positive charge, negative charge. So we have the entire detector is magnetized to about 1.5, 1.3 Tesla. Of course, any detector that you want to use should be easily constructible. It should be modular. So, for example, we want to have 3 modules of each 17 kiloton. That is how we want to build 50 kiloton detector. So, in principle, when the first detector is finished and operational, we can start then, building the other ones and so on. And remember that iCal, the way it is constructed, is mostly sensitive to muons, and they're not sensitive at all to electrons, because electrons leave very few tracks in this detector, because we use very, very thick iron plates, right? So just to give a very quick what all these jargon that we keep talking about, the big detector, the dream that we want to build have is iron calorimeter. So that is how it looks. This structure looks like. We'll see, of course, more details about this. The so-called engineering ICAL. So before we build the big detector, we want to build a prototype which will enable us and give confidence that we can actually build this. By the way, this is what those 3 modules that I now described just now. And even before that, we want to build a very tiny, very tiny so-called mini ICAL detector, which you actually see. These 2 are, of course, is in the graphics, but this is real object that you see here, and it is actually operational in Madurai in our lab called Inter-Institutional Center for High Energy. So you keep hearing about these words ICAL. ICAL is the final big detector that we want to build. Engineering ICAL is what is here, the small one. You will see the specs very soon, and mini ICAL is what I said is right now operational. Just to give you a feel for what these numbers are, sizes are, so on. So you can actually see a table here. Talking about the dimensions. The total dimensions is roughly 15 meters by 16 by 14.5 meters. And you saw that it's a layered structure. There are 150 layers of iron, which is about 6 centimeters thick. There's a gap of about 40 millimeters between the iron plates where you are going to insert the active detector elements. This is the magnetic field. And Deepak mentioned about the resistive plate chambers, roughly nominally of the order of 2 meter by 2 meter size. And you'll be able to kind of get tracks of these particles, let us say, at every 3 centimeters. Okay, you will see that actual resolution for the position will be much better than this, because this is one track. If you send me, I'll be able to give you a position within 3 centimeters. Okay, and of course there are other details here, but what is also important is when you say that RPCs are your main active elements, the question comes, how many of them? What is the total area that you are going to cover? Because there are 150 layers of, let us say, each one of them is 50 meters by 16 meters. So if I have to cover them 150 into 50 into, let us say, into 16, you get 100,000 meters square, okay, of area. These are almost, 15 soccer fields distance. Probably you will see that soon. And the electronics that are required to read this data is almost about 4 million detector channels. You can really see how exciting it is to build, as Deepak mentioned, this experiment completely from an engineering perspective. Okay, ECAL is even not small. Maybe depending on which parameter you're talking about, it's maybe a factor of 100 smaller, but you will still need about 300 RPC detectors and about 40-50,000 electronic channels. But you will see all the elements that you are using are exactly same as ICAL. That is the meaning of engineering ICAL, right? For that matter, even mini ICAL, even though it is extremely small compared to this big detector, but many components that you use here are same as engineering ICAL and same as final detector. And you will use only just 20 odd RPCs, and maybe you will instrument not more than about 3,000 channels. But you will be surprised to see even such a detector can give you a fantastic physics, can give you half a dozen PhDs. So it is not something, when I say small compared to this, but this experiment itself is, reasonably involved, right? Okay, so this is an outreach kind of a slide that I usually make just to get a feeling, meters and kgs and tons and so on. What does it really mean? So if you want to understand in terms of how an ICAL looks like, and you want to compare with Tata Nanos or African elephants, this is how it looks like, right? And in case you still wonder how big this 100,000 meters square that you're going to cover the RPC detectors. So I mentioned to you, it is equivalent to 16 football fields that you tile them together, right? And if you wonder what 4 million detector channels are, typically an ECG machine has about 10 channels on which the signals received and recorded. So now you can kind of imagine what one is talking about. But if I tell you, compared to ECG signals, of course, these are about 1 million times more than ECG number of signals, but also 1 million times faster compared to what ECG signals are supposed to be. So that is the kind of figures you should sink in your mind when somebody talking about engineering, right? Okay, so as I promised, I'll keep showing this detector again and again. But now maybe with a little more details, this detector is consisting of 3 modules. each one of them 150 layers. You can actually see, in case you wonder how big this is the height of a 5-storied building. Okay, and so you build one module at a time. And these green looking objects that you see on either side are of course trolleys by which you can maintain and install this detector. These are the two, there's a guy here standing in this trolley. You can see the size of this person and then get a feel for it. And of course, as I mentioned to you, this is about 50,000 tons of detector. And these purple colored stuff here on the top are actually coils which go around the entire detector through, and that is where you apply you pass current and magnetize this entire detector to magnetic field of about 1.5 Tesla. Okay, so as I said, the way you make it is you use iron plates which are about each weighing about 4 tons and 4 meter by 2 meter in area and about 6 centimeters in thickness, and tile them up one by one, and you can actually see they are interlocked nicely each other. Such layers are initially put on top of a pedestal and then you stack them, but ensure that between each of these there is a gap of 40 centimeters into which later on you start pushing the RPC detectors here. Okay, let me see if I can kind of show you. Okay, I can't find, I don't know why this, maybe I should. Yeah, so just an animation to give you a feeling. So this is the 2.1 kilometer long tunnel, which is actually through which truck carrying, let us say, iron plates are going, and it is actually now parked at the bay where it is supposed to be waiting. And now you can already see that you have a concrete pedestals on which you want to build the first module and the second module and the third module putting together. And here you can see the iron plates are being picked up by a crane, and they're going to be placed one on top of other, and it is always built layer by layer, as I said, and then keeping spacers between each one of them to ensure that later on you can insert the active detector. Okay, of course, here obviously every tile and every layer is put in few seconds, but it takes 3 or 4 years to actually build even one module. Now you can see the purple color stuff, the magnet coils have already gone in, and so these iron plates are special because you can kind of push through them, the copper coils, and you can see very quickly the module 2 and 3 has come out. Now these guys are actually taking in a trolley the fully fabricated particle detectors called resistive plate chambers, and they are actually pushing those into those gaps like a pigeon holes, one RPC at a time, and then they'll go to the next one and so on. Okay, so as I said, the whole animation of course lasts only 10-15 seconds, but it's a long process when you want to build such detectors. So this is what I kind of wanted to give a feeling like when you talk about large RPC, large area RPCs you're going to use in a big number, how big this big is. So if you actually see, I prepared this some time ago, it's a slightly old slide, but nevertheless, it serves the purpose. If you look at all these various high energy physics experiments, cosmic ray experiments, and what is the area of those RPCs that were used, and you can really see it here, compared to even the biggest deployment of RPCs in the LHC, it's actually a factor of 10 larger than that. And of course, there are many differences depending on what is the electrode material. Most people use glass or bakelite. What is the gap between the glasses and how many gaps and modes and so on and so forth. We'll talk about it, but please remember, so this is the kind of challenge that you have. And so the R&D that has started quite some time back, almost 20 years ago, obviously there was no RPC in the country and we really had to start from scratch. Okay, what is RPC? It comes under a class of what you call parallel plate counters, which are actually started, really you can say invented by Kuffel 1949. These class of counters are called PPCs, parallel plate counters. And imagine at that time, he was actually talking about maintaining, machining of 2.5 millimeters gaps. And of course, this is a very, very classic experiment. But what I really want to show is not all this complication, but look at even the, what they call that time uncertainty in reaction time, something like a timing resolution that you are talking here is actually is already coming as a function of the voltage, hitting, kind of nanosecond kind of resolutions at that time. So what, okay, these are Kuffel counters, but little later, Peskov actually picked up this idea, Peskov and, Fedorov what they built is a chamber something like this, which is also a parallel plate counter. But remember, this is made into a chamber, and which is at very, very high pressure, about 10 bar gas pressure. They maintain the kind of gap to be very small, only about 0.1 millimeters, and applied, of course, potential across these two plates. And these are your signal pickup strips. So it works beautifully and gave resolutions of the level of 100 picoseconds. But the problem with this is obviously how well you can maintain this mechanical accuracy, and how to maintain that such a high pressure, and everything is a big problem. So what this people here who actually called kind of father of RPC device now is Santanico and his colleague did in 91 is, actually you can hear from their words, the detector presented in this paper, this is actually the classic paper, is same as Pesta counters, except that they made it a big simplifications in terms of using the cheaper materials, and instead of operating at 10 bar, they try to operate it at let us say atmospheric pressure, close to atmospheric pressure, and then it become a cheaper device. It become very popular, but otherwise it is very similar to this detector that is actually built by Pesta, and it comes under what you call parallel plate avalanche counters. So just give you a very quick schematic of the basic single gap. As for single gap RPC, is you take two electrodes, very high resistive electrodes, could be glass, could be bakelite, as you like, and maintain a gap of, let us say if it is 3 millimeters and gap maybe 2 millimeters, you will see how it is made. And then on the outer surface of the glass, you actually apply some kind of a graphite coating on which you apply a potential, and which is what produces a uniform field between the electrodes. And you flow a special mixture of gas. There are two gas mixtures that I noted down here. Either you use R134 is A is a freon, isobutane, and SF6. This is in this proportion. And there is also another mode which is called argon, isobutane, and R134A, isobutane, and argon. Okay. Now outside this high voltage plane, you actually put an insulator and then put your so-called pickup strips or readout strips. But please remember straight away that the so-called readout strips, which are given as X, readout strips which are given in Y, they're orthogonal to each other, which means if there is a charge particle passing through and producing a, let us say, a signal, we'll see how it is. I'm able to kind of pick up a signal both on X direction and Y direction, or like a crosswire. So with one active medium detector, I'm able to kind of give you both XY position of the charge particle. So this is very nice compared to, let us say, a solution where you have an X-plane detector, you have a Y-plane detector, and so on. You don't have to do that. So just to give you a very simple principle, so if you see a charge particle passing through, of course, this is the gas mixture that I talked to you about. And so electron-ion pairs are produced in the ionization process, and they start drifting. Okay, so the electrons, of course, come towards anode, and then the ions traveling in the opposite direction. Now, all these primary electron clusters, as I said, they start drifting with, let us say, a velocity v simultaneously. And as they go along, of course, they do furthermore have reached, let us say, anode, and it kind of is eliminated. Now, the charge due to this, which is induced on the pickup panels, which are, as we saw, maintained on the outside, it may be given as, let us say, as given by the electrons and as given by the, let us say, ions, right? And they'll be traveling, let us say, one at a drift speed of v, and the other one small v, and the other one is, let us say, a capital V. But ions, of course, they travel much smaller. So you might say that the current which is induced on the panels here is almost entirely due to electrons. So therefore, you can say this is the electron charge, this is the drift speed, and then the distance that you have, the gap you have between the two electrodes, which is what we call either 2 millimeter or 3 millimeters as they propagate. Okay, so the charge that is induced, the signal that you are actually getting on the pickup panels is mostly contributed by electrons here. Okay, a little bit about the dynamics of how you actually control what this avalanche that it happens. You actually use, as I said, a 3-mixture gas. You use R134A is the mainly for ionizing gas, and you use same R134A is also is an electron affinity gas, which can also capture the free electrons which are produced, and you want to localize the electrons rather than spreading the ionization to the entire let us say chamber, which is never a good idea, because then you miss on the position resolution capability. Now, there will be these two reactions also keep happening. I mean, there could be electron attachment, which is actually given here. It could also be recombination of the ions and electrons which are produced, especially before they start taking off their journey. In both those cases, you will, of course, produce, photons, and those photons can actually induce streamer if you don't contain them properly. So isobutane is actually used to kind of kill these photons, which are especially at high energy photons, so that they don't again produce further ionizations laterally in the gap. And SF6 is actually used also to contain the gain of the detector, so that the streamers are maintained, the streamers are avoided. So the gases these 3 mixtures of gases you use in some proportion, which obviously you have to do studies to optimize it, such that you get good gain. At the same time, you also avoid streamers and things like that, because it can spoil the longevity of the detector as well as spoil the position resolution. So you have to really play with these 2 parameters, which are, of course, they're governed by so-called Townsend coefficient and attachment coefficients. Townsend coefficients are, of course, the distance before it travels and hits to the other gas molecule, and the attachment coefficients are, what are the number of attachments that happen for unit distance. So obviously the effective Townsend coefficients is difference between these two. Now, when you say that how I'm actually growing in terms of the avalanche is actually decided by the rate of number of electrons that are produced, which is of course proportional to the this alpha, and also then is the number of primary ionizations that take place. Now, you want to make sure that this space charge, which is produced because you are producing the big cloud of electrons, and they themselves are moving, which is actually influencing the so-called the uniform field that you applied by applying voltage across these electrodes. But at the same time, depending on whether you are talking about close to the electrodes here or close to the way the electron cloud is transferring, the fields are quite different in this area, where it is larger than the uniform field, and at the center, of course, it is slightly smaller. But you want to maintain that you don't want to reach either limit, and you want to maintain the avalanche growth in such a way that they don't become into discharge. So in a way, the Townsend equation, though we say it's alpha n, but alpha itself depends on the field. So therefore, you may have to say as alpha en. Now, the same RPC that you built the way we have described can be operated in the so-called avalanche mode, which is a proportional, semi-proportional mode, which means that I operate with the gas mixture in the high voltage in such a way that when the ionization taking place, now you saw that picture that I described before, and then the avalanche starts kind of moving. And when the electrons move to the anode, of course, you can see that you can already see that you started neutralizing very, very tiny place here. And the ions, of course, reach much later. And then when they reach the anode, the cathode here, you of course get, you can see that some of this local small area get neutralized. Now, when that happens, you will see the field which was at whatever you applied uniform field. And if this field has dropped down suddenly, then you will find that the avalanche actually stops. Now, as the flux inside is actually now varying electrostatic flux, because one is, of course, uniform field. The other one is the field that is produced, a change of field that is produced by the change of the movement of electrons here. And that change of flux in the electrostatic flux is what is actually inducing signals outside the electrodes using Ramos theorem. Now, in the avalanche mode, the signals that are induced on the pickup panels here are relatively smaller, of the order of about 1 picocoulomb. And this we say the gain is, that means compared to the number of primary electrons, what is the total avalanche that happened is of the order of about 1/10 of a billion. Of course, these are good in a way that the charge is less because it increases the detector lifetime, but the signals are small, so you may have to use amplifiers outside, and this is the typical mixture and so on. Some people who do not like operate it at such a low gain, you can actually change the gas mixture and high voltage and so on, and you can actually start seeing a much bigger multiplication, much bigger avalanches taking place, and so much so you actually see a big, it's almost like a conducting electrodes here and producing a huge current between them. The signal that you see induced on the electrodes will be almost about 100 times more than what you will actually see. So you will see much bigger pulses, maybe about 100 picocoulomb instead of 1 picocoulomb. And therefore, you don't need any preamplifier. But the price that you pay is that if I have a very, very high charge regime inside the gas chambers, it is possible that I actually start damaging the inner surfaces of the electrodes, and then that is not good for a long detector life. And it is also sometimes problem for me to get what you call, let us say, the counting rate capability, because a much larger area gets dead here, because whatever you found here, the discharge, this has to be charged only by the power supply which you applied to produce field, right? So that of course takes time, and then the larger the current that I have replenished, the larger the time it takes. So therefore, I will also get a low counting rate capability, which means if you want to use such a detector in accelerator based experiments, then that will be a big disadvantage. So just give you a kind of figures, what are the kind of typical figures you will kind of get from such a detector. Okay, so for example, if I have starting with N0 number of electrons, I will actually get, as I said, exponential alpha beta. This is Townsend, effective Townsend coefficient. And this is where I say these are the number of, let us say, electrons that are reaching at the anode. And the efficiency, intrinsic efficiency is given here, which means the Emax is only depending on the gap, G, as well as, okay, the gas, the mixture that I use, because that is what decides this expression. So, and similarly, the intrinsic time resolution that I get from here is again mostly depending on the drift velocity as well as the Townsend coefficient. It doesn't depend so much on the threshold on which, I'm kind of operating my DAQ system. If you remember, I was kind of telling you that if you operate the detector in the streamer mode, I have a much larger, signal pickup spot, okay, which is again, you can see it is proportional to the Q, the total charge induced, and also, of course, the distance and so on. So, which means that if I want to operate them in the avalanche mode, I get a much better counting rate capability. But if I use in streamer, I have a bigger streamers spots, signal pickup spots, which is of the order of about 0.1 millimeter square, which means my counting rate capability, that means I can't really use it in a high rate environment. Okay, but typically you get for such kind of RPC detectors with whatever parameters I have listed here, you get of the order of about a few picocoulomb charge, you get more than 90% efficiency, close to 1 nanosecond resolution. So these are good qualities of an RPC. Okay, and what we described so far is so-called single gap RPC, but because there is only one gap and these two are electrodes, but you can stack two of them and you make so-called double gap, you can improve the resolution. You could also put a common pickup between the two independent gaps, okay, just a variation of the same. And you might remember Dr. Murmun Devi talked some time back about the so-called multi-gap RPCs. So divide this gap into multiple gaps and it improve on the timing resolution and use for medical and other applications. You could also make the so-called hybrid. Instead of using the glass RPCs, you could also glass electrodes. You could also use other metals. And there is also so-called micro RPC, in which one of the electrodes you kind of make segmented electrode, and then you can get much better resolution. Maybe you can use for X-ray detectors and so on. This is called micro RPCs. These are some geometries. How do I make an RPC? Of course, for making RPCs, you require many materials. Since I told you, you use two glasses which are held parallel to each other, you need such kind of a spacer, like a photo frame, if you look like, on which you put one glass here, another glass at the bottom here, and this decides what is the thickness or the gap between them. You need to flow the gas in and out. So these are what you call gas nozzles. You want to maintain the gap very uniformly, because when you apply voltage, the field is, of course, is depending on what is the gap that you are maintaining between the electrodes. And if the gap is not uniform, of course, you will get different fields at different positions. And that means it's not uniform. The gain is not uniform across, right? So when you actually make this the cartoon of the actual RPC, you can see that these are the spacers that you cover all four sides. These are the gas nozzles, and these are the buttons which are inside between the two glasses, right? I'm only just showing you, and to kind of say that is how delimiting the space between them. Now, I mentioned some time back that the detector which are placed outside the so-called gap are the pickup panels, which are actually allowing you to get the signals on. You can actually see each one of them is roughly about 3 centimeters long. So as I mentioned, one such panel you put, let us say, on the top in this orientation. At the bottom of the gap, you put one orthogonal to this, so that you get a pixel of 3 centimeter by 3 centimeter. When a charge particle pass through, you will be able to kind of get such kind of resolution, right? Okay. Now, when you build like the way I shown, you take glasses, you put them together, you put the spacers around, and you put the pickup panel on the top, and everything put together. You put the electronics that is required to pick up signals from both front. You can call this as the X plane, and you can say this is the Y plane. And so this is a completely assembled so-called 2 meter by 2 meter RPC, and my colleague in Madurai is giving finishing touches before he is going to kind of push this into a stack here. Okay. So, but it of course takes a lot of steps and a lot of care everywhere. Now, when you put on such an RPC, you will see a beautiful pulses like this. These are actually already amplified pulses, but you remember, you see, this is the kind of voltage that you are talking about. This is already amplified to close to about 60 or 70. And the scale is about 20 millivolts. So you have roughly about 6 divisions, about 120 millivolts, but divided by 100 roughly. So it's about 1 millivolt signal is what you're going to see. You should also see what is the time axis. Time axis is 40 nanoseconds. So each division is 40 nanoseconds. You can see how narrow this pulse is. Okay. So how do you know that you actually mastered the design and working, manufacturing of these RPCs? Then you go ahead and build what you call prototype stacks here. I'm showing you 4 of these. And this is one of the first stack that was built in TIFR. This is still working. There are about 12 landings here, and we made 1 meter by 1 meter area RPCs. They are actually stacked. Here you can see there are 12 slots here. There's electronics here. There's a gas system, electronics, and so on. And of course, you can happily track charge particles, which are all available to you, which are cosmic ray muons, which should just go straight through your detector. And as they pass through each one of the landing, your RPC, if it is efficient 100%, you're supposed to get a point there. You will see that. Okay, this is, you can see, is the 2 meter by 2 meter, much longer one, which is also built in TIFR. Another one, 1 meter by 1 meter RPC. This was at VC some time back. Again, 2 meter by 2 meter in Madurai. What did it give you? Several years of running of all these prototypes gave you confidence that you can actually not only understood how to design an RPC, but also their long-term stability. This is the most important. Remember, ICAL experiment has to run for decades. Okay, so only when you know you're confident such a detector works very efficiently as well as for long-term, then you will be able to install it for a neutrino detector. Of course, you also have to, when you build a detector as a student or a faculty, you are supposed to also look at whether each one of these parameters that you build it's working. For example, there are what is called IV characteristics, just like a diode. For example, if you convert an RPC detector the way shown, there is a glass here, there is a bottom glass here, there is a gap here, and if I apply voltage here, and how should it behave? Okay, so until this particular Zinner turns on, I want to see like a VI characteristic, like a ohmic resistance, the way it is actually showing for the spacer. And once the detector starts working, I want to see this as the current getting shooting up. So I want to, as soon as you build a detector, if you apply voltage and look for current, and if it gives you a nice plot like this, you are sure that you built a good detector. That's what every student in iCal does that. After that, you look for whether you are able to get enough charge out of the detector, which means the gain of the detector is quite fine. This is what is called charge distribution for cosmic ray muons. And you can actually see that this is about 1/4 of a picocoulomb, and you got about 200 counts. So roughly about 50, 60 picocoulomb is what you got as a charge. What is also important when you build an RPC, you want to see what is the operating voltage, at what voltage I should operate it. The way you do it is you actually operate this RPC as a function of high voltage that you applied, the field that you applied, and start looking for cosmic ray muon efficiencies, right? So how many cosmic muons out of what you actually gave through a cosmic telescope that the RPC gave you a signal? Now you can obviously see if you operate this at a low field region, obviously you're not very efficient. But once you reach a place where it becomes a kind of rather what we call efficiency plateau, and this is the place where you would like to kind of operate this detector when you push it inside the iCal detector. And as we said, the most important parameter for using RPC is also the timing. We should be able to kind of discriminate whether upgoing or downgoing particle. So I want to kind of look at from a cosmic muon telescope and see whether with reference to a reference which is given by a scintillation detector, what is the spread of the timing that I see on the RPC? And I want to see this at least of the order of 1 or 2 nanoseconds, right? Okay, so all these parameters I need to do it. You need to go even more. You can actually see that such a detector that I shown you, the tracks are, you can really see for a straight going cosmic muon, and it's working beautifully, and it is actually giving you confidence that it is indeed working as a particle detector. And depending on where this cosmic muon is passing through between, with reference to those strips that I told you, pickup strips of 3 centimeters, I should be, if it is going obviously to the middle of, suppose the track is going in the middle of a strip, I want to see that there's only that strip firing. But if it goes slightly to the edge of the strips, the adjoining strip also might fire, and so on and so forth. I want to see such kind of distribution, what we sometimes call multiplicity distribution, whether it is 1 or 2 or 3 and so on. And as I mentioned to you, this is the top view of an RPC, which is mapped due to cosmic muon, and you can really see the place that you have here, which is showing, I mean, the red is, this is the scale efficient, and of course, blue is least efficient. You can really see these yellow dots are actually those spaces where you kept buttons for placing between them for keeping the uniform distance. Otherwise, you can see it is giving you overall, when you take millions of cosmic ray particles through each of the RPCs, and when you can track them and put where it is coming from in the RPC, and you say this is the efficiency, uniformly efficient for the entire 1 meter by 1 meter. I can also go ahead and try to kind of see what is the cosmic ray flux, even using such kind of tiny modules, and you can see these numbers come quite close to what is actually given by standard big detectors that were built and obtained in this. Since the main idea is to get the discrimination, up or downgoing discrimination, you can also see on the surface, of course, you'll always see cosmic ray muons going from only top to bottom, you can actually see all this actually coming only on the right side, and very little on the so-called misidentification. Okay, so this is what I'm kind of trying to show. If you have such a detector, each of the stack, each of this landing, you're going to see one point, which is actually telling you the trajectory of the cosmic muon. Now, as I said, if I take each RPC for a long time, and if I project such a particle trajectory, I can actually see something like what is called a tomography, and you can clearly see these white spots here are the ones which are dead regions, which are caused by the spacers that we use. Otherwise, you can see each of the strip, which is 3 centimeter, and there is a gap of 2 millimeters in between. It's very nicely kind of visible. Okay, even such a tiny small detector, you can actually track cosmic muons, which are multiple muons within about 2 meter by 2 meter detector, and you can see they're beautifully tracked. It's not just single muon tracks, but even double. RPCs are very good in terms of for using it for detectors like iCal, because you need for very, very large area and very thin, because they are only about 10 millimeter thin. And of course, with material, etc., it will go to about 25 or 26 millimeters. And they're very flexible detector. I can design the geometry the way I like. I can do XY. I can change the pitch of the pickup panels and so on. I can use the same RPC for tracking, calorimetry, as well as muon detectors. I get excellent timing, as I told you, and they are all used from simple common materials. Remember, high energy physics detectors are very large in number, very high in a count. So you can't really build with very expensive materials. It's very easy to build, as you saw, and very, very suitable. Ultimately, you don't build 30,000 RPCs in your lab. You have to build in a industry. And there are many other nice characteristics. I don't want to go for want of time, but RPCs are really nice, suitable detectors for such a detector. Of course, since RPCs are based on gas is the detector media. So you also have to build so-called gas systems. Gas systems are the units where it takes those mixtures of gas in cylinder and mix them in the proportion that you want and flow through the RPCs. Okay. But remember, if you build the big ICAL, will require about 200,000 liters of gas, and you can't really, throw the gas into the atmosphere. And also, I mean, even of course, it's not allowed, but even if it's allowed, it is a waste of money, right? So what you do is, when the gas is mixed together, when it is flown through your detector here, what is shown, but after all, it is only used as a detection medium. It is not something consumed in that sense. So take the gas out and take it out and, maybe clean it a little bit, because due to a lot of leaks and going through the pipe, etc., there may be some little contaminants, moisture, oxygen, or water. Purify it using molecular sieves and other materials and push the gas back. So you will be using only a few small percent of new gas every time. And this is what we call closed loop gas system. And that is what is kind of developed. Okay. Now I'll skip some of these plots, slides, because of want of time. Now I want to go to and just tell you a few things about, in terms of electronics, what is it required. Remember, when you have a stack like this, what you are actually asking is essentially want to see what is the path of these charged particles that are passing through. So suppose this is your ICAL detector. If I see either muons passing through or a neutrino coming in and then interacting and producing, let us say, muon charged particles, you want to track them. To track means, as it is traveling, you want to see what are the coordinates of X coordinate, Y coordinate, and Z coordinate. Of course, Z coordinate is given by the so-called layer. You remember we talked about 150 layers, right? But X and Y are given by the so-called pickup panels, which are orthogonal to each other. We talked about. Okay. So the information that I want is, at every level, which is one Z coordinates, I want to give you one X and Y, and another X and Y, another X and Y, and so on. So that you will be able to kind of do a fit of this depending on what you want to do, whether it is, with magnetic field, without, and so on and so forth. So this is one piece of information. The other piece of information, as I said, as the particle is, let us say, passing through, we should be able to get a time stamp, which means with reference to the passing of the particle, at what time the particle entered here, what time it entered here, what time it entered here, what time it entered here. Then if it is in this increasing order of time, then I know this particle is going from top to bottom. And if it is other way, it will go from bottom to top. So I will be able to kind of give you a, directionality capability. So which means there are two informations. One is, as I said, so-called latch. That means giving you XY coordinate. The other thing is compared to, let us say, passage of the particle, what is the time that it took to hit this layer, next layer and next layer and next layer and so on. And if I see a cosmic muon particle, if it is going all the way down, and if it's going through all 150 layers, you will have 150 such informations. Okay, so that is the main information that you want to get it. So of course we get down and say that this is my RPC. These signals may not be very big. I would like to kind of have an amplifier here. And then I want to signal process the signal that are coming out of this RPC need to be kind of, you remember we said you need XY coordinates. you need to kind of measure the time difference between the particle passing through and hitting the detector, and so many other, monitoring parameters. So you kind of block and, break down the electronics requirement into this. But remember, you also have to generate what is called a trigger. Trigger is a system which is telling you when to record data. Otherwise, there may be a lot of other spurious events. You don't want to trigger them. And this is the most important system. So you need to also build an electronic system which is going to decide based on the track of the particle or the topology of the hits, whether this is an interesting event or not interesting, right? This is the electronics. So the first thing first, so there will be students who will sit down and say that, okay, this is the requirements that I need. This is the amplification I need. This is what is required for my detector. And they make a block level diagram. Say I need an amplifier here. I need a comparator because I want to convert an analog signal into digital signal, and so on and so forth, a multiplexer and so on. So this is the basic drawing that is required. Very simple textbookish drawing. But what is important is, unfortunately, you can't go to local market and buy an amplifier for you. So you have to design, because the signals are very small, they're very fast, such kind of very, very high bandwidth ICs or op amps or something are not available in the market. So some of our students go and sit and design what they call application specific integrated IC. Starting from very basic electronic circuitry, they actually go and design this chip by themselves, okay? And then we go to a foundry. Unfortunately, we don't have good foundries in the country. We go out somewhere, and maybe European foundries or somewhere, and get these chips fabricated. So these chips that you see here, these are not bought in local market, but actually built, designed by the collaboration, and of course, manufactured in a IC foundry. Now you can really see there are large number of such chips which are produced by INO within the collaboration itself, okay? Initially, we started with some what you call hybrid chips. Now they are called ASIC chips, both for analog, for amplifiers, etc. And you remember I was telling you the ones that measure the very tiny difference, that so-called time to digital converters. This is again designed and developed inside the INO collaboration. If you want to measure a particle passing through with reference to where it hit each one of those landings, if this is a start signal which is produced by so-called trigger system, what I'm actually asking you to measure difference between these two, right? So if I provide a clock to you, I'm actually asking you to measure how many full clocks it is. And then obviously the start can come anywhere and the stop can come anywhere. So I should be able to measure this T1 here. I should be able to measure this T2 here and say the time difference between them is T1, which is total this pulse here, and T3, and then minus T2, right? Because you don't want to count that extra one. It looks very classical and very simple. There are many configurations and many ways people can build so-called digital application specific integrated circuits. One that you see it is here. But just remember that what you are actually asking is to distinguish something like 125 picoseconds resolution. So you are measuring this difference at a level of 1/4 of, let us say, a nanosecond, okay? Which is very important because that is what gives you a capability to be able to kind of give you a directionality of this signal. So this is again produced in the collaboration. Now, there is another thing before I go quickly out of this electronics, is we also heavily use what you call field programmable gate arrays. They are like circuits which come to you when you buy it. There is no circuit inside. You can decide what circuit you want to put that inside, and then download just like the way you download a program from somewhere. And that field programmable gate array becomes a digital circuit all by itself. And then you can start using, you can put a lot of complexity inside. You can even put microprocessors inside, microcontrollers inside, and so on and so forth. Okay, so such kind of a big, modern field programmable gate arrays onto where you put all the digital logic inside, digital converter here, and then the data that is digitized is actually coming through, a network, which I will show in the next slide. Okay, and everything inside that field programmable gate array can be programmed. So somebody can actually write to do what data acquisition software that they want to do. And when you build the entire system, it looks like this. It is a very funny looking triangle-like board, because you will see soon why we need to take very small space for the electronics, because you want to get good area for the detector active volume, right? So you see this vertical wall in which the entire signals from one RPC are getting into. This is the time to digital converter where you measure the tiny time differences. And this is the field programmable gate array into which you put all the electronics that you require. The digitized data will come through this chip and come through this connector. This connector, you will be familiar, it is same as your Ethernet connector. And this board is supplying power, which will go on the top of this. Just compare this with your pencil size. It will tell you this is just about 10 centimeter by 10 centimeter, that to a triangle, right? Why such a small thing? Now you compare. This is your RPC, which is 2 meter by 2 meter. In that area, you're only occupying this little space for the triangle here, and this little space for power supply, which produces field, okay? Which produces, which you want to produce uniform field, you apply high voltage here. Rest of the area is all you want to keep it for the active detector volume. So this white area, everything is active. This is the top view of an RPC. Of course, you can see the amplifiers that we talked about for the Y side marked here, and for the X side, these rectangles are here. So that are the only area which is so-called dead area. Rest of everything inside a big RPC is maximize that. Okay. I want to quickly go to an important system. I hope I have. Can I take about 10 minutes, Deepak?
All right. Yes. Yes. Please.
Okay. So of course you want to detect neutrino interactions that are taking place, right? So they, depending on whether they are charge current events or the neutral current events, you typically produce, for example, let us say muons, which are produced long tracks inside the detectors, and they go through many layers of RPCs. So therefore, it is probably one way of detecting them. The other thing is those which when you want to look for hadrons, they don't go through long tracks because you are using very thick material. So they might actually shower out and confine to only few layers. So when I want to say that I am actually looking at both for charged particles, muon-like particles, as well as hadrons, I should have a strategy where I should be able to track them, or I should be able to recognize them inside my detector volume, right? When you want to estimate the neutrino energy, okay, for this muon, of course, it is easy to do it because you have magnetized detector, and then you have XY coordinates for each one of them. You reconstruct and get the tracks. Okay, from the track, from the magnetic field, radius of curvature, you can get what is the energy. Whereas for the hadrons, you actually have to see how many such pixels got fired, and from there you may be able to kind of get what is the hadron energy. So it is indirectly kind of obtained. So the choice of so-called trigger criteria based on whether I'm talking about the charge current events or your neutral current events or muon-like events, that is what is dependent only on the hits that you saw. What are the hit pattern? We don't use any other any other information. Obviously, I want to have a very minimum detection threshold so that I don't miss neutrino-like event. At the same time, if my threshold is too small, then I get a lot of chance coincidence. Chance coincidence is where just because there are random signals coming from the detector, by combination of that, I should not produce wrong signals. So how you produce trigger? Some signals are produced right in the RPC detector itself, so that they are called trigger primitives, so-called level 0. Some basic decisions about whether or not this is useful or not is produced right at the RPC one detector element. And segment is a part of ICAL detector. So the next level, so these signals go to the segment level where higher decisions are taken. And finally, the global trigger produces at a module level. Okay. So for example, if I say this is my track, it is passing through 6 layers. And if I say, tell me that out of 6 layers, at least 5 layers must have at least one hit. Okay. So that is out of 6 layers, at least 5 layers must have at least one hit. Okay. That is M cross N by P. You can see that I'll be able to pick up all of those muons which are passing through because they typically hit one. But I'm also taking care once in a while, one of the detector might be inefficient. So I'm not asking 6 out of 6, but let us say 5 out of 6. But let us say somebody is looking at little hadronic kind of interactions. So I'm asking, no, now I want to, for example, in this, if I say you look for 4 out of 6, but let us say see 2 hits. It doesn't generate trigger because you have only 1, 2, and 3 of them have 2 hits. Okay. In some cases, if it is only confining to only fewer layers, then I have to generate another condition, maybe say 5 out of that, maybe 2, maybe 2 of them. Maybe I'll be then able to get more shower-like triggers, and here more muon-like triggers. I have to really decide and put all those conditions in these various combinations. But I don't have time here, but I also said it's also important when you choose what is your trigger criteria, you also don't want to generate all spurious so-called chance coincident trigger. So therefore, you have to be very, very careful about those things, okay? So when we put together, so this is your, let us say, a segment of your RPCs, you bring all those detector here, and depending on whether it is a 1 hit, 2 simultaneous hit, 3 simultaneous hit, 4 simultaneous hits, 4 I mean 4 strips, 3 strips, 2 strips, and each one of them you allocate that trigger decision by a separate board here, and all of them put together, finally they decide what is your the final trigger system, the global trigger system. Once the trigger is produced, what I should do? I should, once the global trigger is produced, the backend system should receive the trigger and then say, oh, at this moment of time, I have actually received a trigger. Immediately, that trigger is also going to all the RPC units, because that trigger goes back to them. And each RPC, you remember the triangular board that is actually picking up, collecting all the data, time data, pixel data, everything, and immediately started transmitting data, just like PCs transmitting, sending data to the server. All this data comes to the pipe here. They're called event data buffers. They can come at any order because they come through Ethernet. And this particular piece of hardware is going to look at the time of the recording, the time of the trigger here, compare that, and if it is satisfied, saying that, this RPC, this data, they all belong to a particular trigger, and then make what you call event. You build an event. Event is for that particular trigger, which are the RPCs, which are giving you that data back to you. So all the data comes to you, and then finally build an event and put it on your storage. Of course, you will also produce the signals and display the tracks and so on the thing. Just remember, it's not just the ASICs and ICs, etc. that we build. We even go ahead and build even the power supplies, high voltage power supplies that are required to power the RPCs. This is a power supply which is looking a little ugly to you because it is not packaged. But this particular unit, again, looking only 10 centimeter by 10 centimeter, taking, let us say, a voltage of about 12 volts, it can actually give you plus or minus 6 kilovolts, okay, plus 6, minus 6 on both, which you can connect to your RPC on 2 electrodes, and you will be able to produce, let us say, 10 to 12 kilovolts between the 2 electrodes and produce the field that you require. This entire unit is also designed and fabricated, and we need, of course, 30,000-40,000 of those things. Even power supplies have to be produced to specifications that are required. You don't buy. So you can see a big collage of all the developments that you see here. And as Deepak said, the RPC story in India started in 2001, September 28. Here you can actually see a logbook, which is actually a page of that I've shown. But today you can see there are so many institutions. They have later on built RPCs, RPC lab. They also built for many other experiments. The one that's shown on right are the students and postdocs that went out of INO and built their own RPC labs in their new institutions. Of course, when you start RPCs like this, which you build and characterize in the lab, you have to also go to industry and fabricate them in large numbers, right? So, for example, many methods that I was telling to you, saying that you paint, you put a graphite coat on that so that you can apply voltage and so on and so forth. How do you do it? You can't take a brush and start painting. So you have to actually make such kind of gadgets where it should be able to kind of paint on a glass. This is a 2 meter by 2 meter glass. You can see how easily it is able to paint X and Y positions. You can also paint it using what is called a screen printing. You can see this is 2 meter by 2 meter glass on which in an industry, glass industry, this is actually being painted and cured, and also the measurements are made on this. And some of the students actually do projects and say, depending on what is the resistivity of the paint that I shown here, what is it here? What is the kind of pickup or crosstalk that is going to happen from one channel to another channel? This is very important. You can see a result here. which tells you that depending on how fine the pickup strips that you will be able to use. For example, I said initially I said 30 millimeter wide strips, but if you go down to 3 millimeter wide strips, you can actually get a 0.5 millimeter resolution. If you use 5 millimeter pickup strips, you can get 1 millimeter resolution. So this is what you can actually get subsequently after you get the basic raw data. So these are the kind of studies the students do. After you get the glass, of course, again, you don't go and make things the way you make it in the lab, everything manually. Build a robot to do that. So you can actually see that there is a glass which is sitting at the bottom, and these buttons, if you remember, I mentioned to you, they're all placed here, they're glued here, and this machine one button at a time, going and placing them, going and putting glue, and then and go and so on and so forth, right? And after you build the entire gap, of course, you should also ensure that it is all leak proof. And another student actually built this system using an embedded system. Nowadays people use Arduinos and Raspberry Pis and things like that, and very beautiful system which can kind of find out very, very minute leaks in the full gap of 2 meter by 2 meter by 2 millimeters. Okay. After all that hard work, of course, we built this tiny little baby, what I called mini iCal, which is now a reality. You can really see that these are the iron plates that I showed you. These are the last 2 meter by 2 meter RPCs which are inserted, and this is the coils that is actually producing the magnetic field, the same magnetic field that I talked to you about. And there is a big ancillary system which also cools these copper coils. There is a cross section to which you cool low conductivity water, chilled water, so that it doesn't increase the temperature when you flow thousands of amps of current, right? Okay, and so you can see it has every component that is required for a big detector, but except that this is about 4 meter by 4 meter and only about 10 layers here. But every component, single component of RPC is actually demonstrated. And you will feel very happy when you magnetize such a detector, and when you see the cosmic muons. Of course, this is on surface, and the bend, and students working on it and able to kind of look at the momentum, when they can calculate such for these muons, you'll feel very happy that the whole detector is working the way it's working, and it is now actually scaling up in industry is what is kind of required. So I'm sorry I took a little more time. I just want to end by saying, development and characterization of very large area glass RPC is actually completed. It's a very, very exciting journey. And they're, of course, now being produced in multiple industries, especially glass industries. We also build closed loop gas systems. And I showed you now for the bigger detectors, of course, you need to scale it up. And all the electronics that I very quickly went through are actually designed. And now we are waiting for them. Prototypes are all limited quantities purchased. And the detectors and electronics, which are actually being used in many, many iCal prototypes, I've shown you 4 or 5 prototypes, and including the mini iCal, which I showed you the last. That is what is giving you a confidence that the whole system, when it is put together, it really works. So useful experience gained, and a number of problems which we identified during the mini iCal operation itself. That is very useful, because when you want to scale 20 to 300, 300 to 30,000, this experience becomes very important. Okay, so I want to thank all of you. Thank you for your attention.
Thank you, Dr. Satya, for your nice talk. So now the session is open for questions. So if you have a question, please raise your hand.
I think Shailesh has a question.
All right, yeah. Shailesh can, yeah, I think he is gone now. Oh, okay, yeah. So,
hello.
Yeah, we can hear you.
Yeah, I have a couple of questions.
Okay.
In the Covenant range detector, they had delayed coincidence, which proved to be a better technique to remove other possible background events. So is there similar possibility for iCal where there could be some other delayed coincidences?
Well, it all depends on what detector that you design and what is the process that happens inside the detector, right? So, I mean, what kind of technique that you want to use very much depends on what is the detector technique itself. There you can really see you use let us say the prompt the photons and then delayed the neutron captures, right? So for them, you can't say that if you capture only the 2 photons that are coming out and you declare them as an event, because that could always happen through many other processes. But when you actually tag them together, you are nailing down saying that this is the process that happens in my active detector volume and this is how I detect it. In this case, the idea is different. Here you are using a magnetized iron calorimeter. Now, as the, either plain cosmic muon, which happens once in a while, maybe pass through, or let us say the charge particles which are produced due to interactions taking place, you only have to measure their kind of, what I said is their coordinates. And you also have to measure the timing because you want to see, let us say, whether they're going top to bottom or bottom to top. So this is the schema of things here are different than the schema of things that they had for their detector. It all goes by, for example, the same detector, suppose you say, I also want to look for very, very slowly moving particles, for example, in the iCal. Okay, then maybe your concept will be different. Here, they're all relativistic particles, so you can put a window and then look within that window, for a trigger, right? Because even such a big detector, you can put a one microseconds window and things like that, and provided your chance coincidence rate doesn't become too large. But if you say that I want to look for very slowly passing magnetic monopoles or some such thing, then I can't brute force have large window, right? Then it is possible that I may have to look for such a sequence or some other smart way of capturing this. So it all goes by what is the detector concept and how you want to build the overall detector and the trigger system and the instrumentation.
And my other question is, like the individual electric components like the transistors and all the things which we are using, they have their own individual time delays of the order of maybe picoseconds or nanoseconds. So there are a lot of them in the circuitry. So can we still get the nanosecond resolution in our detector?
That's a very good question, actually. As you said, that typically depending on how you design your ASIC, right? There could be a lot of jitter if you kind of call. For example, for analog system, it is different. For digital systems, it is different. Let us first look at very quickly about the analog system. Analog system, you use like what you saw. One of them is an amplifier circuit, right? Okay. So, which is in a way, it's like an op-amp, but op-amp built with, let us say, transistors, a large number of them. Now, depending on how you connect between one to another, there will be always a jitter between, let us say, one stage of an amplifier to the other stage of amplifier, even within a chip, not on a PCB or tracks or wires or something like that. Okay. Whereas if you go to the digital system, it is a little more complicated because many times the way you route them, there are like gates ultimately. Okay. Now you also have to look at what you call a routing, just like you do on a PCB, you route one track from one to another. You also have to route inside an IC how the signal is passing by. Okay. It's true that you have to match to a large extent. Thankfully, many of these VLSI design tools, okay, sometimes they're called EDA tools. They allow you to able to simulate these systems to such a great level. In fact, they use many times Monte Carlo simulation to level where these multiple path delays are optimized in such a way that it will give you the best possible input to output delays. So, of course, there are parameters that you have to play with. Okay, chip size versus power versus number of channels versus the speed versus. There are many parameters, but you can say that okay, I would like to maximize my jitter. I would like to minimize my power. I would like to minimize whatever. And then these simulations really work very well to you. And the question is really nice in the sense the RPC detector in this case plus all the electronic chain that you see from amplifier to all the way there, when you actually do a characterization study in test stands, the number that you come to you, 1 nanosecond, 2 nanoseconds, or whatever sigma, is the one which is actually the sum total of all the jitter that you see in the system. So this is detector plus electronics. Of course, there are also other parameters you should worry about. One of the most deadly thing is so-called time walk. The time walk is the smaller charged signal, higher charged signal, they do not have the same time profile. So the bigger signals, are produced faster compared to the smaller signals. So they become kind of very slow. Now that difference itself can kill the resolution that you are looking at in the RPC. So therefore you have to be really careful to overcome all these differences. Yes, but that is a nice question that you can't just simply overlook. Yes, both detector side and electronic side people have to come together.
Thank you very much.
Yeah.
All right. So we'll take a question from YouTube.
Okay.
So first question is from Sadashiv Sahu. So
Okay.
the question is, why do we need a continuous flow of gas rather than static gas pressure in RPC? Does it have any role with size of RPC?
Does it what?
Have any role with size of RPC?
Yeah, so his question is about the so-called, packed detectors, which are, typically, classically, would have seen many proportional counters, ionization counters, many of them, versus the counters that we have here, which are operated at very high, let us say, electric fields, very small, electrode gaps. And the process that you are looking at here is also very fast processes, not like olden days where you had like rise times of few hundred nanoseconds. You are looking at rise time of the order of a nanosecond or two. Okay, so you require to maintain certain purity of gas so that otherwise, the signals can be very kinky. The signal, if it is contaminated with some gas, some other, outside, could be also giving you very funny pulses. So in order to ensure that the gas volume that you are projecting or presenting to charge particles is uniform and it is always, very clean. So it becomes very important you kind of use them as a flow type. Now, that is just a broad answer. But in this case, what becomes important is that when you have, I told you something like 200,000 liters of gas and literally hundreds of kilometers of actual linear area, linear distances of pressure of gas pipes, if you can look at. Now, even if you are few ppm level kind of even gas tightness, if you can maintain, still there will be a lot of area where there can be kind of the leak possible. So in which case, one of the easiest way, I mean, you can say I'll make zero leak detectors. Okay, if you can make zero leak detectors, yes, then there is no need. But it's very, very difficult when you do an industrial process. So another best way, because you are actually not operating them at a very high pressure, you are operating almost close to the atmospheric pressure. So another simple method is to start flowing with, let us say, a few millimeter water column with a very low flow and flush the gas from input to output, so that even if there are some small leaks that happened in between, then the gas still is fresh. So therefore, the operation will be better. Now, it's important when you do flow type, you don't want to waste the gas that is coming out, as I said. So the best thing is actually take the gas out and actually purify and put back. So it becomes important to maintain closed loop system. So the question that he asked at the end, yes, it becomes more important when you have larger detector than small one. I mean, you can make a 1 centimeter by 1 centimeter detector and seal it like mad, and you don't have to really do flow type gas. Of course, we also did studies about what is the minimum flow of gas that is required per, let us say, unit time. So roughly 1 volume change per day. That means roughly about 8 liters, 2 meter by 2 meter by 2 millimeters is about 8 liters of gas. If you do per day is good enough. We in fact even sealed one, some gas RPCs for months together. We did not actually find so much of problem, except that the RPCs had leaks. If there's no leak, then you can actually maintain in the, of course, there is a small fraction of radical formation that happens due to signal formation itself, ionization and avalanche. And if you operate them in streamer mode, you have bigger problem of radicals being formed and you need to kind of flush them out. But if you operate in proportional mode, that problem is much less. We can't hear you, Deepak. Deepak, we can't hear you.
Yeah, now, yes.
Now we can hear.
Okay, so one more question from the same person. So he has asked, in the animation of iCal construction, if we need to repair any part, typically at the region, do we need to disassemble all the
yeah. So this anyway is Murphy's law. So I didn't go into that detector construction. I just went very quickly. One module is, let us say, 8 roads. You know, roads are just in parallel lines. Into each road, you push. Each road is 16 meters. So 2 meter is 2 meter by 2 meter is an RPC. So you can push 8 RPCs in one. The way we do it is, if you remember that drawing that I gave, there are trolleys on left side and right side. You push 4 RPCs on one side, 4 on the other side, right? Now, why I said Murphy's law is, it is possible the deepest one inside might go bad. Okay. So out of 30,000, if you see even 1% of them goes bad, it is a big task. Normally what we do is, if the RPCs are having some minor problems, we live with them for some time. We don't go and replace that each small problem, one gap, one channel, 2 channels, etc. But if an entire RPC goes bad because of, let us say, high voltage is bad or something else, electronics is bad, obviously we have to take it out. So the way you take it out, if you see those trolleys which are going, and you saw in the animation, so you have to pull them out. 3 of them, you have to pull them out, stack it in the trolley, take a good one, of course, along with that. So push that one and then bring the faulty one down and repair it down. You cannot repair anything 15 meters above. So unfortunately, it is, yes, it is a painful thing. By the way, but this is how all high energy physicists around the world work. There is no shortcut. If it is only at the tabletop experiment, then you can do repairs easily, or you can send to the manufacturer, they will repair and give you. But in high energy physics experiments, you have to repair yourself. That's why the students and everybody should know what the detector is, what electronics is, how they work, how they don't. Many of our students, actually, they spend all the time in looking at data and to tell you where are all things going bad. Even with that tiny detector I showed you, we learned a lot of it, how to operate it in a long-term way.
One more question from YouTube from the same person. The question is, can we replace RPCs with plastic scintillators and silicon photomultipliers? Okay.
By the way, I hope these are not all INO students. So for INO students, you can wait till the little end. You can take maybe the other students. Okay. Nevertheless, I will go ahead. Who is this? Who asked this question? Okay. It doesn't matter.
Sadashiv Sahu.
Sadashiv Sahu. Okay. Yes, in principle, you are right, Sadashiv. It's a planar detector. I mean, when we went for this baseline design of RPC at that time, all we needed is tile-like detectors so that you can insert them, right? That is the most important thing. And also, it's important. I rushed through that, but it's also important if it is thin enough so that then you occupy less space, right? You can fill it up with more iron. Okay. Now, if you want to compare, for example, there are problems with RPCs. One of the biggest problem is, of course, you have to flow gas, right? So that issue is there. And similarly, you have to generate high voltage locally and so on and so forth. Now, that problems won't be there for scintillators. Scintillators, once you push inside, put a fiber inside, etc., they stay there. They don't require any gas or anything, no high voltage and so on and so forth. The silicon photomultipliers were not existing when the INO was thought about it. They, of course, become reality much later. But even now, they have become very cheap. But it's not that if you want, something like 4 million silicon PMs, etc., they're reasonably costly. And also remember that you need to do segmentation. Now, if you look at scintillators, you want to do X and Y segmentation for it to get X and Y channels, right? We remember how the RPC is. So you have 64 segments channels on one side, 64 on X side. So you also have to design the scintillator in such a way that it actually it has a segmented scintillator. Of course, you can use like strips packed together. You can also do vertical isolation and then make them optically separate. There are techniques to do. In principle, yes. In principle, you can use scintillation tiles or extruded scintillators read by wavelength shifting fibers. At the end of this one, you use silicon PMs. It is possible. But to a certain extent, one has to also look at cost and things like that, the benefits. Yeah, that's right.
All right. So now we take a question from Zoom, Bala Subramaniam. So I will unmute.
Yeah.
Yeah.
Hello.
Yes. Please.
Okay. Hi. Good evening, everyone. So why is this 1.3 Tesla magnetic field? Is there any characteristic reason behind that?
Okay. Actually, the expert on this is actually in the audience. But maybe I'll just start and maybe Professor Datar can add. I mean, what is the magnetic field that requires to a certain extent depends on what is the physics that you're looking at, right? So ideally, you are going to kind of do, what are you going to do? You are actually going to have iron plates, you're going to magnetize them, and you're going to look at XY coordinates of the track as they're going. Now, depending on the momentum of the particle that you're looking at, either you will have a very curved kind of a track, or maybe the radius of curvature, what I meant, could be larger, could be smaller, based on the momentum of the particle, higher or lower. Okay, so now there are some problems you will start facing. It's very nice to track particles which are going, cosmic muons which are going without magnetic field, but when you start having magnetic field, when it starts kind of bending, it is possible that your position resolutions are not as good as you wanted to see. Of course, you can also use timing information that I talked about also to improve to some extent the reconstruction efficiencies. Okay, but if I can have larger magnetic field, probably I'll have another handle on this. Or so what is the point? I mean, can I have 4 Tesla magnetic field, for example, 3 Tesla magnetic field? No, but it also makes things bulky. It makes operation, because this is a conventional magnet. This is not a superconducting magnet. So things become very bulky and very difficult to operate if you go to very high. So you would like to kind of have roughly the rule of, the basic specification that worked about it is from the physics studies is about 90% of the detector volume, you would like to have a magnetic field, which is, let us say, a Tesla and above. Okay. So with that kind of a picture, the whole system is being designed. But as I said, I would like to take some opinion from Professor Datar on this.
Okay, I think, you have basically answered the question. So ideally, we would like to have as high a field as possible so as to measure the momentum accurately. Actually, momentum by charge. Because you have mu plus and mu minus. But on the other hand, iron saturates at about 2 Tesla. And of course, if you have such big, iron plates manufactured in industry, they saturate. They start bending over. So you have a B versus H curve, which starts bending over already at about 1.4, 1.5 Tesla. Now, if you want to go to 1.6 Tesla, let's say, then you might require 20 or 30% more current, because this is an electromagnet. So the power requirement will go up by 60%, and so on. If you want another, 1.7 Tesla, it becomes even more expensive. So this average, or the over 90% area, as he said, of field of the order of 1.3, 1.4 Tesla seems to be adequate. In fact, the simulation people at the time we were designing this said that even a 1 Tesla field is okay. So 1.4 Tesla seems to be a reasonable number. And we can get that with low carbon steel that is manufactured in the country rather easily. So that one can go really at some BH curve which is extremely sharp and which starts bending over at 1.8 Tesla. But then that iron is extremely expensive. It's about, I think, 3 or 4 times as expensive.
And also difficult to handle.
Yeah. So we have to also look at practical considerations. We have to keep cost within reasonable bounds. But at the same time, we have to get the detector to perform as we want it to.
Wanted.
So this is in experimental situations, it's always a compromise. And this seems to be a reasonable compromise. I think I might also want to comment on the plastic versus RPC. So at the time that we started, the plastic detector was about 3 times as more expensive. And already the RPCs contribute a reasonable fraction of the total cost. So 3 times more expensive would have been.
No
costs are coming down. And,
no SAPMs at that time.
Yeah.
So you had problem in terms of, segmentation and how to read, and each tube was few $100s and so on. Yeah.
So with the price you have to pay with the glass RPC, that it's a little more difficult to handle. Yeah. But if we have learned the techniques on a small scale, we will have to do this on a larger scale.
Also operational cost, and then the fact that you have to flow the gas. And somebody asked this question about
the running cost versus capital cost.
Yeah. Thank you, sir.
Hello, I have one more question. What about the data collections? Are you going to, have a grid computer or?
Sorry, because lack of time, I couldn't spend much time on the backend side. No, we don't have to go to cloud computing. Unlike the petabytes of data that the LHC pours in, the data that comes from here, as you could somewhat imagine, is very small. For example, you are only recording, really speaking, just 1 bit per strip. So you have 64 plus 64, so 128 bits, right? Maximum. That is for the position information. And let us say take another 24 bits or 32 bits even for the time TDC. But if you look at the so-called occupancy, means typically out of your 3 million channels, how many channels are going to fire by simple cosmic muons or muons produced neutrino interactions or even showers? Okay, that will be very, very small. So I can assure you, out of 30,000 RPCs which are manning your detector, a small, maybe a few % of them are actually going to have data fired. Now, once a RPC fired, the total package of data is only about 600 bytes. And believe me, out of the 600 bytes, most of them is actually header. Very little actual data. So the data that comes out, can be recorded very easily. But again, you look at what is this trigger rate that you will see underground. If you see on surface, yes. But when you go underground, if you calculate, probably it will be like, less than 10 hertz. That is the trigger rate for the big detector. So most of the time you are just sitting idle and only doing the monitoring of ensuring that all 30,000 RPCs, electronics, everything is working fine. And once in a while, when the event comes, you actually trigger, the system will tell you, you go and record the data and send to the backend. So to summarize, you don't require a very, very big server or in a big storage. Of course, we are planning to have the basic system right at the detector and one system in Madurai, and also system which will allow all the collaborators wherever they are to be able to access the data. So there will be a sizable amount of computer infrastructure, but nowhere near like LHC or any other experiment, not at all like what you anticipate in terms of, cloud. Very small data.
Okay, so thank you.
Yeah.
All right. So I think we'll go for one last question, or shall we? How many questions shall we take?
I see 2 hands on.
So we'll ask Ravindra to ask.
Okay.
Hello, sir. Thank you very much for your very excellent talk. So I have a general question that since you have discussed about the tracking, muon tracking in your talk, generally on the surfaces while we do, earth surfaces while we do muon tracking experiments, we have high chances of getting the combinatorial background.
Yes.
So, in case of our underground, for example, in case of INO, do we have that combinatorial background chances? And if we have, what we will do further?
Now, I think you're talking about when you say it's like sometimes we call noise rates, sometimes we call background rates of individual, let's say strips in this case, which are picking up data from the RPCs. Now, when you see on surface, quite a lot of it also come from cosmic background And also it comes from all the materials, tracer of radioactive materials around with what you make the RPCs or anything like that. When you go underground, of course, your cosmic flux might come down, and so those rates might be coming down. But the ones that are produced in the rock or produced within the materials with which you make, that will remain more or less same. That is not going to kind of change. Okay, so when you design the trigger system, for example, which is the one which get affected by the combinatorics that you talked about. Okay, so parameters like what is the window that you want to look for coincidence, what is the multiplicity that you want to ask for, and how well you want to segment it, etc. That those are the things that you have in your hand to kind of bring down the chance coincidence rate. But again, for experiments like INO or any cosmic experiments, this is not too big a problem, because you have quite a few such handles to kind of contain the chance coincidence rates in this case. So only even if like mini iCal or engineering iCal, when you build on surface, that trigger rates could be 8K, 10K, even 8 by 8 meter long area. But when you go underground, the rates come down, and then when you put enough cut, you also will be able to bring down the rate. But see, it's important also to keep an eye on what is the optimum threshold for trigger. Obviously, you don't want to miss an event just because you wanted to reduce the chance coincidence rate, right? So therefore, sometimes people do say, what is, data to tape? What is my capacity? Sometimes even people used to hit the trigger rate based on that. But nowadays, you have plenty of data space. So people don't mind actually doing so-called triggerless system, where you take all the data that is coming from RPCs and record everything and do your trigger criteria offline, so that you can run whatever you like after that. You don't miss any data. So it is quite possible for experiments like INO. One could also think about that. But there are other issues, like you have to have high-speed data lines from front end to back end. And the architecture of the DAQ system is entirely different between triggered and triggerless system. Yeah.
Okay, sir. Thank you so much for
But by the way, you also need certain amount of background rates, what you call, because those are the ones through using which you are actually monitoring the gas pressure, the high voltage, the temperature, the humidity, all those parameters you monitor only because there is certain counting rate that you can depend on and get characterization between the rates and affecting these parameters. Actually, if the detectors are all silent except for neutrino interactions, you don't really know whether at that time they are sleeping or they're up and working. So you require this. Also, it's a very useful thing to have some rates at the background. And also record some junk events, doesn't matter. You can always throw them rather than missing an event.
Yeah, but for example, yeah, I think, no, I mean, if there is a chance of, if I am looking for the track from one muon, if I get hit from other muons in the first track, second muon hit in the first track, so can we remove that?
Yeah, you want to record multiple
event?
muon events, right? Why do you want to remove them? I mean, it all depends on your trigger, right? You saw even in such a small detector, Surya, one of our students, he actually showed those multiple muon events, right? So your trigger has to accommodate. Your trigger has to accommodate, and it will accommodate, because if the condition is only so-called P into M by P into L by M or whatever, I mean, that condition will decide what is your trigger. So if there are two muons, multiple muons, through-going muons, hadronic kind of events, large angle events, you have to have every trigger subsystem looking for this. And when you put them together, global trigger should take care of all sort of events that you envisage. By the way, modern day people don't anymore, fix the trigger and say, this is my trigger system. By using these programmable chips, tomorrow if somebody wants a new trigger, you don't have to go and keep changing the wires. You just send the new lookup tables to the FPGAs. They start implementing new trigger conditions. That is how LHC or any other accelerator experiments do. So you have to have trigger condition extremely flexible. How do you know after you get the data, a physicist will say, yeah, no, I think your trigger is too shallow or it is too strict. I would like to change it. You cannot say, no, I will change 3 million wires in my system. So it's important to keep that. It's very, trigger system is the most important system of any high energy or cosmic or nuclear, whatever, I mean, experiments. There's no doubt. It's even more complex for accelerators.
Okay, yeah. Thank you so much, sir.
Yeah.
So we'll take one last question from Rohan. Rohan, please go ahead.
You have to unmute. Okay.
Yes, gone. Oh yeah, he's there. Rohan, yeah.
Yeah. Hello, can you speak a little louder, please?
Yes, sir. I have a general doubt. Like at INO.
No, we can't hear you. Please. Hello.
Good evening, sir.
No, it's not clear still.
Some of the experiments are carried out at cryogenic temperature. So,
Can you please type your question so that we can read?
Actually, Deepak, I can hear him. Maybe I will repeat the question.
All right. Oh, yeah. Okay.
Okay, sir. Some of the experiments at INO is carried out at cryogenic temperature. So I would like to ask that suppose that in bolometer experiment we are using a preamplifier where JFETs are used at 120 Kelvin. But if we take a normal JFET which we are using in our practical labs, it has a temperature range from -60 to 100 degrees, 125 degrees Celsius. So how this shift? So same transistors are used at cryogenic temperatures. So how you calibrate or how you manage with these devices? So will you use a special grade device or the same components?
No. Okay, so this question is about cryogenic detectors like NDPD or any other futuristic detectors, which will also come up in INO or otherwise. When you develop electronics for that, some front end, let us say, has to be at the cryogenic temperatures. So the FETs that you normally buy, whether or not that will match to the electronics requirements for such a detector. Is that the question?
No, my question is very general, like the components which we are using at room temperatures, can the same component be used at cryogenic temperatures?
No. I think there are, you mentioned about FETs. Once again, I think probably Professor Datar will be the best person to answer, but let me just start by saying that nowadays there are specific designs of the FETs that people make for varieties of applications. It's not like something so-called, any FET will work for any system. Not only for cryogenics, even, there are FETs which are used for VLS electronics. There are FETs which are used for very, very, electrometer kind of circuitry, very, very high impedances circuit, which are required for low current measurement systems and so on. There are many special purpose. In fact, some of them, even the material that is used for making them also, there are companies which make specific FETs for specific applications, I know for sure. But I'm not sure whether, no, if your question is whether ordinary FETs can be used for these applications, the answer is no. The answer is no, but I think Professor Datar probably can give you a more authentic answer because he also worked on cryogenic detectors. Sir, you have to unmute your mic.
Yeah. Now I can. So I think we are allowed to unmute. Okay. No, what you said is correct. Any old FET will not do. It has to be, a chosen FET and also something that works at cryogenic temperatures.
Yes.
It's, typically, I don't know if you are familiar with the, high purity germanium detectors. They don't operate at Kelvin temperatures. They operate at about liquid nitrogen temperature, 77. But there also you have to choose the right FETs. And it's possible to do that. And of course, when you go to Kelvin temperatures or even 110 millikelvin, then there is a different set, I think, that has to be used, and care has to be taken on various fronts. not only
Also
on
the
electronic, but also mechanical things and
mechanical.
so on, contacts and so
Also
on.
the contacts and wires, and you don't want to use them as thermal antennas.
Correct.
Yes.
So, but yes, I mean, there is a sufficient amount of experience nowadays in that you can use these. Also, I think for the very low temperature things, you also use superconducting devices to amplify and detect signals. Squids.
This is Rohan. The question from Rohan, right?
Yes.
You might want to go and listen once to Professor Vandana Nanal's talk. I'm not sure if she described them in that detail because she gave a talk on the same forum about the NDPD detector and the other experimental R&D. But incidentally, one of her students right now is actually designing electronics for the cryogenic. So if you listen to that talk, maybe something will come up.
I don't think it is there so much in the talk, but he can certainly write to that group.
Right.
That's there on the TIFR website, in the DNAP, or maybe you just.
I can even give the name of the student. His name is Vishal Vatsa. Vishal Vatsa or Vatsa, I don't know. Vishal Vatsa. So you can write to him. You can see TIFR People's Finder. He is the person who is actually working right now for his thesis. Yeah.
Okay, sir. Thank you, sir.
There are, or Rohan, you have any more questions, or is that it? Because you're okay.
Yeah, he pulled that on.
All right. Okay. So I think there are no more questions. So from Zoom, do you want to take questions from YouTube or?
Yeah, I think they're already. It's already 8 o'clock. Actually, we
all right. So I think there are all TIFR students.
Yeah, if they're TIFR, we can. They can always ask me anytime. If there are anybody outside TIFR and has something very specific, I don't have any problem, but I don't want to keep you holding.
Okay. Specific questions, I think we can take one and then.
Okay.
So, what is track A and track B in the KGF experiment? Where is the neutrino interacting?
Neutrino, okay. So this is it's coming from the rock, which is I think a meter or so off. Okay, and the track that you see up, I don't know if I should show.
Your screen is not shared.
Yeah, can you see it now?
Yeah.
Okay. Yeah, okay. So this track here, this track up here, right? This track is the muon that is produced in the W production. Okay, and the origin is expected to be from the rock that is surrounding here. And this track here is supposed to be a muon decay from the W. Okay, so this is the muon. I mean, both are muon, but this is the muon that is produced in the inelastic production, and this is the muon decayed from W bottom. And you can actually see that when they cross these layers, you can see then this one also gave you NFT signal, and this one also, and here also. But in this case, only the center line, and this one actually gave you the hits in the NFTs. So these two tracks. Okay, so this is the muon produced, and this is decayed muon.
Okay, there's some more questions, but I think we can take it answer them offline on YouTube directly.
Okay.
So if there are no more questions, I think we will end the session, but we would like to inform about the list of talks that we will be having next week. I think I can share my screen now, or I don't know if, oh yeah. Yeah. So on Monday we have a talk by Professor Kajuri Mazumdar.
Not Monday, Friday. Friday.
Friday, yes, Friday, yeah, about LHC. And on Monday, 8th June, we have a talk by one of the founding fathers of INO, the story of the neutrino and INO. And then on Wednesday, we have a talk by Professor Poonam Mehta from JNU on neutrino oscillations and matter-antimatter asymmetry. And on 12th, we have a talk by Professor T.P. Singh on quantum mechanics and gravity. So we hope to see you all there. So wish you all a very good night. Thank you.
Thank you, Deepak.
Yeah, thanks.